Hello everyone. So in the last class we had spoken about Rns configuration. We had seen how molecules can be detected as R or S, and the optical activity of the molecule will depend upon that. So basically they are going to shift the light towards right direction or left direction, very much depends upon what is their configuration, right? So a molecule which is optically active can represent itself by R, S, these kind of representations. Similar, it's exactly in the same way how we say that you if you have let's say geometrical isomerism existing in the molecule, then it can be represented by cis and trans. Now we're talking about enantiomers. So enantiomers are again type of isomers of optical compounds or optically active compounds. Now what exactly are the enantiomers? Let's understand. So enantiomers are the chiral molecules. Chiral molecules means the ones which have the chirality in it, basically, which are optically active. So enantiomers are optically active molecules that are mirror images of one another. So basically any optically active compound and its mirror image are called as enantiomers. When you talk about these mirror images, these are non-superimposable. That we have already learnt earlier also, that when you talk about chirality means non-superimposability. So if anything is chiral, that means its mirror image will be non-superimposable on each other. So basically a chiral compound and its mirror image, these two substances are called as enantiomers of each other. These are non-superimposable mirror images of each other. So when you keep a molecule on the top of its image, you will find they are not matching anywhere. I mean, they are not able to completely indulge and become one. That is what the superimposability means. So we may have one chiral atom here, we may have more than one chiral atom here, we may not have chiral atom at all. So that also we had discussed that chiral center's presence is something which does not affect the chirality of the molecule. So here enantiomers are nothing else but a molecule and its mirror image. Both of them must be optically active and non-superimposable. These two substances are called as enantiomers. Okay, so let's talk about their characteristics also. So in an enantiomeric pair, that means pair of enantiomers, both must be individually optically active. So basically both should be showing optical activity. Now you may have a thought in your mind that is it possible that they won't have any optical activity? When one molecule has an optical activity, then the molecule also must have the optical activity. But we will see cases going forward. So basically here the mandatory condition is both the molecules, one, the original molecule and its mirror image, both must be individually optically active. That means individually they must be chiral and non-superimposable on each other. Both the compounds will have exactly same physical properties. That means you cannot differentiate them on the basis of their boiling point, melting point, or you talk about freezing point, density, refractive index. So all these physical properties cannot be the basis of separation of these molecules. So basically by any physical method like distillation or sublimation or so and so, there are so many physical methods which you can use to separate the substances or differentiate between them if they have difference in any of the physical property. But here you cannot use any physical method to separate them out. Now where does the difference come? Difference comes in the chemical properties. So you will find in some of the reactions both of these isomers will behave differently, or their chemical properties will differ from each other. Physical properties will not. Their appearance, their boiling points, freezing points, color, everything will look exactly same. So we will be able to differentiate between them only on the basis of their chemical properties, not on the basis of physical properties. Now when I say that their chemical properties will be different, which specific chemical properties will be different? Will all chemical properties will be different? No. So most of the chemical properties will be same. Even in the terms of chemical properties, you cannot say that they will be completely different in terms of chemical reactions. Only and only the reactions which they are going to do with any optically active compound. That means the molecule which you have taken, I mean, let's say there are two reactions. We have two enantiomers. Let's say A is one compound and its mirror image is B. Now if I react A with C, C itself is a chiral compound. Okay, and I react B with C, and this C is again the chiral compound. So the reaction products what you'll get when A will react with C and B will react with C will be different. So basically, themselves should be optically active, and your another compound should be optically active. If two optically active compounds will react, then you will figure out the difference in the chemical reaction. So you can have identical chemical properties in most of the cases, except the cases where reaction is going to be with an optically active reagent. So basically, one your molecule which you are referring to and the another molecule which you have taken for reaction, that should also be optically active, and these two will react, then then you will find a difference in the products forming. So as I mentioned, if I have two enantiomers A and B and there is a C compound which is chiral or optically active, rather than writing chiral, let me just write it optically active, which you'll be able to understand much better. So if the molecule is, if this is optically active, this is optically active, we know that A is also optically active and B is also optically active, then they will produce different type of results in both cases, and this will help you in differentiating between A and B. Okay, so this is about the properties of enantiomers. Let's see how enantiomers look like. So we have seen the molecules and their mirror images, but now we will just list down some examples so that you can visualize, you can understand in terms of R and S also. We have understood how to assign Rns configuration, and in terms of Rns, how will you be able to figure out the enantiomers, or there are other set of compounds which are called diastereomers. There are third set of compounds which are called as Meso Compounds. We are going to learn about all the three compounds. So how will you give them, how will you give a compound a configuration, and how will you differentiate between them in terms of enantiomers and diastereomers and Meso Compounds on the basis of their configuration. Okay, so let's say I have this molecule, I have drawn a Fischer projection. This is my chiral carbon. I have a COH on it, I have OH on it, I have CH3, and it's 4 different groups are there. If I have to write the configuration of this molecule, what we will do, we will try to find out the priorities first. So OH will have first priority, COH will have second priority, and CH3 will have third priority. Now when we'll go, this is going in anti-clockwise direction, but look at the hydrogen's positioning, which is the least priority. This is on the horizontal line. So anti-clockwise means R over here. So we have got the R configuration in this case. Okay. Now if I draw the mirror image of this compound, what will happen? This OH will come here, hydrogen will go there, COH will remain at COH position, CH3 will remain at CH3 position. So this is the mirror image of this molecule. Now let's see whether the configuration is same or changing. So if I draw the configuration here, this is 1, this is 2, this is 3, and this is going clockwise. And in case of clockwise, if you have the lowest priority group on the horizontal line, then the configuration becomes S. So now the configuration is S. So now we know that the first compound which we have taken is R and its mirror image is S. So configuration is completely opposite. Even their optical activities are going to be completely opposite. So if one is dextrorotatory, another is going to be levorotatory. The angle in which they tilt the light or the plane polarized light, that will remain same. Let's say if they are tilting the light with 20 degrees, so in that case one will be plus 20 degree, one will be minus 20 degrees. So amount of tiltation will still remain the same, amount of deviation will still remain the same, or moving towards left or right will still remain the same. Only difference will be the direction. One will be moving into the right direction, another will be moving into left direction. Okay. Now let me make another variation in the same molecule. Basically, I'll just switch the molecules here and there, and then we'll see the Fischer projection. So let's say if I write the OH here, and hydrogen here, CH3 here, and COH here. If you look at the molecular formula will still remain the same. Molecular formula is not changing, only the Fischer projection alignment of the molecules is changing. Now I'll try to give it the Rns configuration. So I have first, the first priority here, second priority here, and third priority here. So what we are going, how we are going? We are going again clockwise. If we are going clockwise and the hydrogen is on the horizontal line, then again it has become what? It has become S. Now look at it very carefully. This compound, the second one and a third one, they look different when you look at it at the first time, but their configuration comes exactly same. So Fischer projection can be written in many ways basically. So it depends on who is the viewer, from where they are viewing, and then which two particular groups are in front of a viewer and which two groups are away from the viewer. That also depends upon the direction of the viewer also. Okay, so you can draw the Fischer projection in many different ways. So what is the criteria to judge whether the molecule or different Fischer projections what you have formed are for the same molecule or are same molecule or different molecular isomers of each other? We just look at the configuration. If configuration is same, no matter how different they look from each other, if the configuration remains same, they are identical. Okay, I'll show you one more way how to check the identical. I told you if there are double switches happening, in that case the configuration doesn't change. So my molecule is this. I have COOH, I have OH, I have CH3, and I have hydrogen. This is my compound. Now to convert into third, what can I do is I can just switch the position of OH and CH3. If I'll do so, what I'll get is I'll get COOH over here, CH3 over here, OH over here, and hydrogen over here. Right? So now what we are going to do is we are going to do one more switch between CH3 and hydrogen. If I do this switch, so there are two switches happen, one switch here and second switch here. So now the compound will become COOH, H here, CH3 here, and OH here. So now two switches, that means the configuration must not change. That's what we had understood in R and S also. So here, because the double switches happen, we have just shifted the molecules in such a way that twice the exchanges happen, and that's the reason the configuration has not changed, and the molecule is yet again the same, not a different isomer also. And that is the reason why second and third are exactly same, though they look different, but their configuration is same. Till the time the configuration is same, that means the molecule is also exactly same. Okay, so if somebody asks us to find out the relation between the first molecule and the second molecule, first molecule is one compound, second is a mirror image of it, and it is non-superimposable and has a different configuration, and both are optically active. So this first and second, the relation between first and second is they are enantiomers. Okay, so or you can say these are enantiomer isomers of each other. Second and third, if you talk about, then what's happening? In case of second and third, they are identical. Why? Because both are possessing the same configuration. Now look at the first and third one. I told you that it should be mirror image, the enantiomer should be mirror image, should be individually optically active, and should be non-superimposable mirror images. Now third molecule, this molecule doesn't look like the mirror image of first, but if you do the double switch, you will get the second and you will get the mirror image, right? So that's the reason we say that the second and third are identical, and hence we can consider 1 and 3 also as enantiomers of each other. Okay, though it doesn't look like they are mirror images of each other, but after switching you can make it the mirror image, and that mirror image will be optically active, non-superimposable mirror image. Hence we will say first and third are also enantiomers of each other. Okay, now let's talk about the next term, that is diastereomers. I hope you would have understood what is enantiomers. Now we are going to talk about the second category, and then once we learn both the categories, then we will implement the concept of enantiomers and diastereomers in the questions directly. Okay, so let's understand what are diastereomers. So diastereomers are the ones which are non-mirror images of each other. So they are non-mirror images, but apart from being non-mirror images, they are also like they are non-superimposable. So non-superimposable, non-mirror images of each other. That means they cannot be after double switch or even number of switches. You cannot convert into mirror image. That's the thing. Okay, so you don't have to get confused between the first and third. What I did in the last slide, first and third were enantiomers of each other, though they were not looking like mirror images. But if you do the double switch or if you do the even number of switch, you will get a mirror image out of it, right? But what we are referring to here is that if I have two compounds A and B, A is not the mirror image of B and B is not the mirror image of E, and even after doing the even number of switches, you cannot convert into mirror image. That is what exactly we are trying to say. They should be non-mirror images and non-superimposable on each other. But here the condition which was required or mandatory in the enantiomers, that both the molecules must be individually optically active, that condition is not here. They both can be optically active, can be optically inactive, can be one optically active, one optically inactive. So there is no restriction over the optical activity over here. So the two compounds which you are referring to when you are trying to find out the relation between them, if they are called as diastereomer, that means that optical activity is not mandatory. Only thing which is mandatory, they should not be mirror images of each other, and even after even number of switches, the one should not be able to convert it into the mirror image, and these should be non-superimposable. So such kind of compounds are called as diastereomers. I think theory you will be able to understand, but you won't be able to relate much. So we will see the question, we will understand what exactly we are trying to say. Before that, we'll just see the characteristics of diastereomers. So first characteristic is, in pair of diastereomers, both may be optically active, inactive, or combination of active and inactive. This is something which I have exactly told you just now, that their optical activity is not mandatory to be a diastereomer or a pair of diastereomers. Okay. Next is they will have different physical properties. So that means their boiling point will be different, their melting point will be different, their refractive index will be different, their densities will be different, and hence you can use the physical methods to separate them out. So basically, diastereomers can be easily separated through the physical methods, which was not possible in enantiomers. And when we talk about diastereomers, which comes first in our mind? When we talk about the alkenes, okay, cis and trans of alkenes, the alkenes which show geometrical isomerism, those geometrical isomers are diastereomers of each other, because they are no way mirror images of each other, but also non-superimposable. Okay, and we don't even look at the optical activity in that case, right? So they are non-superimposable, non-mirror images. Their boiling points, melting points, density, dipole moment, everything is different with respect to each other, and hence can be easily separated. Okay, the diastereomers can exist in the compounds where at least two chiral centers should be there. So when you talk about one type of diastereomers are the ones which show geometrical isomerism, but if we talk about such kind of alkanes which we are dealing with, in that case you need the two chiral centers to make a diastereomer. Okay, so basically the compounds which have minimum two chiral centers, only those compounds can show diastereomerism. Otherwise, it is directly geometrical isomers, which are also called as diastereomers. But apart from that, there is no midway. It is not like one chiral center is there and hence they can show they can form their diastereomers. That is not possible. So for one single chiral center, there can be only one type of mirror image, and that will be enantiomer, will not be anything else. So let's understand. Let's see some examples over here. So before that, you just write it over here. Okay, GI are also diastereomers of each other. Diastereomers of each other. Okay, now what I have done is I have taken a compound and we have just switched the positions of the molecules here and there in the Fischer projection, and then we have seen the relation between the different compounds, what can be formed through that particular compound. So I have taken the compound with two chiral centers. So I have one over here, and the molecules which are present on this carbon is COH on the top, COH at the bottom, H and OH on both the carbons. Now, if this is the first compound, right? Now, if you look at the rotation, or you can say look at the configuration of this molecule is anti-clockwise, and because it is anti-clockwise, this is R, because hydrogen is on horizontal line. Similarly, for the down one also, the configuration is R. So we got the first compound has configuration R and R. Look at the second compound. Second compound is absolutely the mirror image of the first one. So OH here, hydrogen there, and OH here. That's how it is in COH and COH. And even you can see the configuration also is completely opposite. So the previous one, both the chiral centers were RR, whereas here the two chiral carbons what we have are SS. So configuration is completely opposite. Right? Now look at the third one. Now I have made a small change. Now what we have done is, till now in first and second we had made the mirror images of each other. Now we have done small change. Now one side both the hydrogens are there, another side both the OH are there. And now if I want to check the configuration here, one carbon possess R and another carbon possess S. Okay, so neither this compound is mirror image of first nor it is the mirror image of second. So these are the compounds. So basically just understand, now the first and third are no mirror images of each other, neither their configuration matches. Similarly, for the second one also, second and third neither are the mirror images of each other, nor their configuration matches. Okay, so such kind of molecule, the relation between first and third and second and third is called as diastereomers, because they are non-mirror images, non-superimposable. So this compound, third one is non-superimposable on first. Similarly, third is non-superimposable on second, and they are optically active also, and they have different configuration also. They are not non-mirror images, non-superimposable. Okay, now look at the fourth one. So fourth one, again I have made a small change. Now OH at one side and hydrogen on the another side as compared to the previous third case, and now the configuration has become S and R. Okay, and then the fifth more compound I have made. What change we have done? We have done a switching between H and COH. Now COH is here on the horizontal line, whereas the hydrogen is on the vertical. And so small variations we have done to see what kind of relationship these molecules will build, because the molecular formula is not going to change. Only the spatial arrangement is changing of the functional groups or the groups which are present on the compound. right? So I have just now told you first and second, their configurations are completely opposite and they are mirror images of each other and they are optically active, hence non-superimposable, and hence first and second are enantiomers of each other. Now let's look at the second and fifth. So second, if you look at, has the configuration of S and S. If you look at the fifth one also has the configuration of S and S. Both are S and S, and hence we generally write it as this is second carbon. So second carbon will be written as 2R and the 2S, and on the third carbon the configuration is S, so we write 3S. So we generally represent it as 2S comma 3S. 2 means second carbon is S and third carbon is S. That's how we write it when we have to write it for the multiple chiral center thing, and we have to individually find out the configuration for each chiral center. In that case, we write it this way whenever we are naming a compound. So if you compare the second and third, the configurations are exactly same. Though there are switches happened, and that's how the second has become fifth one. But because the configuration is exactly same, we call them identical molecules. Now, if you compare between first and fifth, now first and fifth don't look like that they are mirror images of each other, but don't go by just mirror image. Look at the configuration also. Configuration is completely opposite. For mirror images, the configuration will be completely opposite and the compound will be optically active and non-superimposable. So this is optically active also, and the configuration has completely reverted also, and that's why first and fifth will be called as enantiomers of each other. Though the fifth one doesn't look like it is a mirror image, but you can do the double switches or even number of switches and you can convert it into a mirror image of the first one, and that is why second and fifth are called as identical molecules. Okay. Now let's talk about the third one and fourth one. So third one and fourth one, just try to understand and relate. So third one and fourth one are mirror images of each other. OH here is on the right side on the third one, and the fourth one it is left side, and the hydrogens which were on left now are on the right side. So third and fourth, they are mirror images of each other. They are non-superimposable, but whether they are optically active or not, that we have to check. Optical activity doesn't seems to be here in case of third and fourth both, because if you see, there is a plane of symmetry. I'll just draw the plane of symmetry through a different color. Okay, let's draw it with orange. So look at this. If I put a mirror over here, won't I get the exact don't you think that the upper part and the lower part are the mirror images of each other? They are. So this compound is not optically active. Exactly same way. When you talk about the fourth one, they are mirror images of each other, but they are not optically active. And for enantiomers, the condition is they should be mirror images, they should be individually, both the molecules should be optically active, and they should be non-superimposable on each other. Then only the molecule will be called as enantiomer. But this is not happening in this case. Third and fourth are not optically active due to the POS present over there, and hence these will be simply called as mirror images rather than being called as enantiomers. Okay. Now compare between first and fourth. First has R and R configuration, and the fourth has S and R configuration. So a lot of difference in the configuration. Secondly, they are not even mirror images of each other, but they are non-superimposable. Also, along with that, one is optically active, another is optically not active, and hence this pair will be called as diastereomers. What was the condition for diastereomers? You do not require the optical activity, but they should be non-mirror images and non-superimposable on each other, and that's what exactly is happening in first and fourth case. Similarly, second and fourth also behaves in the same manner. First and third also behaves in the same manner. Second and third also behaves in the same manner. So in all the cases, they have different configurations, and they are not mirror images of each other. One is optically active, another is optically inactive, and hence these pairs will be called as diastereomers. Okay, so I have told you first and fifth are enantiomers, first and second are enantiomers, and when you talk about the third and fourth, it looks like they're enantiomers, but they are not, because they're optically not active. So just don't go by the configuration. Also check whether the optical activity is present or not. Why it is optically inactive? Because the POS is present over here, and this is what exactly is enantiomers and diastereomers are. So I hope you would have understood the concept of diastereomers and enantiomers. In the next question, what we are going to discuss now, you will tell me the relationship, or you will pause the video, you will write the relationship, and then you will confirm it with mine, what I have written the relations between different compounds. So here I have taken the compound. Again, two chiral centers are there, one is here, and there are COH and COO, CH3 groups are present, H and OH are present on each carbon. So both the carbons, the second one and the third one are chiral carbons. optical activity is present because there is no POS and no COS over here. Okay. Now we have to see the relation between all of these molecules, which are exactly the same molecule with respect to the molecular formula, just their spatial arrangement is changing, and that's why we have to figure out the relation between them. Okay, so first of all, let's figure out the kind of configuration they possess. In first compound, the configuration is 2R 3R. In the second compound, the configuration is again 2R 3R. In the third case, the configuration is 2S and 3S. In the case of fourth, the configuration is 2R and 3S. In the case of fifth, the configuration is 2S and 3R. And in case of sixth, the configuration is 2S and 3S. So these are the configurations of the chiral centers in the case of these compounds. Now let's figure out the relation between them. So look at the first one and the second one. First one and second one. First of all, look at the configuration. Both the configurations are exactly same. If the configuration is same, the molecule becomes identical. So this is identical. Now look at second and third one, or let's compare the first with all of others, and then we will go for second to third and third to fourth and fourth to fifth. So first molecule, the compound 1 and compound third, what relation they possess? Now look at the configuration. This is 2R and 3R, and this is 2S and 3S. So configuration is completely opposite. Now we have to see whether they are optically active or not. If both the molecules are individually optically active, then they will be enantiomers. So because in the first case there is no plane of symmetry or center of symmetry, this looks like this is optically active. Look at the third one. Here again there is no plane of symmetry and no center of symmetry, hence this is also optically active. So these first and third will be called as enantiomers. Now first and fourth, configuration itself is weird. In the first case 2R 3R, in the fourth case 2R 3, so configuration is completely different, hence they are definitely not going to be mirror images of each other. And let's see whether this is optically active or not. But even if they are, even the molecule is not optically active, we are trying to find out the relation. And for diastereomers, optical activity is not even a condition. So first and fourth are going to be diastereomers. Okay. Now first and fifth, again the configuration is differing. It's not completely opposite. It's not completely same, and hence the relation between first and fifth is going to be diastereomers. Okay. Now let's come to first and sixth. In case of first and sixth, complete inversion of the configuration is there. But in the first case, you don't have any optical activity. In second, in fifth, do we have any optical activity? Yeah, this is also optically active because it doesn't have POS or COS. So first and sixth are going to be enantiomers. Exactly the same way, let's find out the relation between second and third, second and fourth, second and fifth, and second and sixth. Second and third configuration is completely opposite. Are they look like mirror images of each other? Let's see. Yes, they look like mirror images of each other, but non-superimposable, so this is enantiomers. Okay, second and fourth configuration is varying from one chiral center, so definitely not going to be enantiomers, and they are going to be diastereomers. Okay, second and fifth configuration is again random. One chiral center, it is varying configuration, hence again this is going to be a diastereomer. Second and sixth configuration is completely opposite, but are they mirror images of each other? The configuration is exactly opposite, and if I do a double switch, one is here and one is here, I'll get a mirror image of this molecule. I'll get the molecule which will be mirror image of second one, and hence these will be enantiomers. Okay, now let's talk about the third one with fourth, third with fifth, and third with sixth. The third and fourth random configurations, diastereomers. Third and fifth, the configuration again random, diastereomer. Third and sixth configuration is exactly same and hence identical. Now for fourth and fifth, fourth and sixth. In case of fourth and fifth, configurations are completely opposite. R is S now and S is R now, so completely opposite configuration. Let's see whether they are mirror images of each other. So yes, they are mirror images of each other. Do they possess optical activity? Yes, they do, because there is no plane of symmetry and COS, because even if you cut it from here, there are two different groups, COH and COCH3 over here. So no plane of symmetry, no COS, so that means they are optically active. So if you talk about the relation between fourth and fifth, this is again enantiomers. I'm just writing ENANT. Now fourth and sixth configuration is random, so they are diastereomers. This is how you have to find out the relation between the molecules when the question is given. I hope you will be able to figure out which ones are enantiomers and which one are diastereomers. For enantiomers, you have to check two things. One is the configuration. Second, whether they are mirror images of each other or not. Even the mirror images is something which is not very important, but you have to see whether they are optically active or not. And after even number of switches, if the molecule is not mirror image, after even switches, is it becoming mirror image or not? So these three things you will have to check. In case of diastereomers, you just have to check the configuration must differ randomly, and then one is optically active, another is optically inactive, or both are optically inactive, or both are optically active. It won't matter at all. If the compounds are not mirror images of each other and non-superimposable, then these will be diastereomers. This is about enantiomers and diastereomers. Now I'll give you some questions. Find out the relation between them. These are the questions. Try out on your own. Wait, pause the video, try it on your own, and then I will discuss the answers for these. So here in this first question, we'll try to find out the configuration first. So Cl is 1, the lower part is 2, and the CH3 is 3. So clockwise your movement is, and hence the configuration will be as same as the case for the second chiral center. Exactly same way you will try it over here and you will find RNR configuration. So now we know that the configurations are completely opposite. We have to check whether they are mirror images of each other or not. Okay, before mirror image, first let's check whether they are optically active or not. So is the molecule optically active? Yes, seems like this is optically active, no POS, no COS. This is also optically active. Now we have to find out whether the molecules are mirror images of each other or not. Right now it looks like they're not mirror images, but I'll do a double switch and check whether I can form a mirror image out of it or not. So if I'll do the switch over here and a switch over here, the molecule which I'll get is CH3, Cl, hydrogen, Cl, and CH3, which is exactly the mirror image of this first one, and hence the relationship between them is enantiomers. Okay, now look at the next one. Next one also find out the configuration. So configuration I have written it for you over here. For the first carbon it is R, second is S. Again, first is S and second is R. So configuration is completely opposite with respect to each other. Whether they are optically active or not, let's figure out. So if I cut it from here, it seems like there is a plane of symmetry in the first compound, so it is optically inactive. This is optically inactive. As there is no way I can call them enantiomers, let's see what else can we call them. So if I do, so what I can do is, okay, in this compound now, if I do a double switch like this and like this, the molecule which I'll get will be COOH, OH and H, OH and H and COOH, right? This is what exactly I'm getting. The configuration here is S and R. Now just look at it. Because they are optically, this molecule is also optically inactive. So whether they are mirror images of each other, they are mirror images, but if you rotate it, basically, even if they are mirror images, they are identical. Basically, mirror images, when the optical activity is not there, that means the mirror images are going to be identical. So if you rotate it to 180 degree, I told you, when you rotate the Fischer projection to 180 degrees, then also it gives you the exactly same molecule. Or you do the double switch, gives you exactly same molecule. So this is symmetric from up and down. Okay, and hence I can say these are identical compounds. Though it looks like the first carbon here is R and here is S, but you look at the molecule completely. Isn't this same? Isn't this COH, OH and H? If I rotate to 180 degree, again it will become exactly same thing. And 180 degree rotation of a Fischer projection doesn't change the configuration. Okay, so when you are rotating it, white is becoming the exact same compound because it is optically inactive. If it would be optically inactive, then configuration wouldn't have changed. Now here rotation at 180 degree, the configuration is changing. Configuration is not changing. Basically, the first carbon is becoming R and the second carbon is becoming S on rotation. But if it would be an optically active compound, in that case, if you would have rotated it to 180 degree, then there wouldn't be any change in terms of the configuration. So configuration is actually not changing here also. It is identical up and down. You just rotate it and it will become the same molecule. Okay. So we will not call them just mirror images. We will call them identical compounds. Now look at the next one. Next one, two chiral centers, one is here, one is here. Again, two chiral centers, one is here, one is here. I do not need to find out the Rns over here. I can just see whether the optical activity is there or not, because for these kind of compounds, it is very difficult to find out Rns. So, optical activity is there. Is there any plane of symmetry? No plane of, yeah, there is a plane of symmetry here. My bad. So there is a plane of symmetry over here. You cut it from here, and these will be two same compounds. Now see whether there is a plane of symmetry in this compound or not. So in this compound in trans, I don't think there is a plane of symmetry. No plane of symmetry, no POS, no COS. Here POS is there and no COS. So this is optically inactive compound, and this is optically active compound, though they are mirror images. So they are not mirror images, and their configuration differs, and one is optically active, one is optically inactive. So this is diastereomers. Second, the question of a second type of compounds are quite common to be asked because these are a little confusing. So you keep your mental eye open, think in all the directions. So you may get a question where they will just mention mirror images, and there will be an option where they'll mention identical. So here in the case of second, the answer has to be identical, not only mirror images. Okay, so that is what you have to check, whether the compound after rotation at 180 degrees is changing the configuration and is becoming exactly same as the given compound or not. Now look at the next compound. So this is both the chlorines are up or both the chlorines are down. Are they make a different compound altogether? No, it's not. No, the viewer is looking from up or viewer is looking from down, or you can say viewer is fixed and you rotate the molecule. First of all, these two molecules are going to be identical according to me just by looking at it. Why? Because the configuration is not changing. This is also cis and this is also cis. Right, so basically configuration is exactly same, and they have plane of symmetry. Right, so they're optically inactive. My bad, optically inactive. This is also optically inactive, and even though it looks like that in one case the two chlorines are towards the viewer, and in another case two chlorines are away from the viewer, but they are exactly same, they're identical. I mean, it doesn't matter because my viewer is here. You rotate the molecule, you rotate a cis molecule, will it become a trans? No, it will not, it will still remain the cis. Okay, so these are identical molecules. Now go to the question number fifth. In question number fifth, we have an even membered ring where the two groups are opposite in opposite direction with respect to each other. If you remember, we had spoken about the even numbered rings in case of when we were checking the optical activity. I told you whenever you have an even membered ring, and no matter if the two groups, same groups, are present in the opposite directions, no matter in cis form or in the trans form, they will always possess plane of symmetry. So there will be plane of symmetry here. This will be like this, and in this case it will be like this. Right, so both the molecules have plane of symmetry, hence optically inactive. Both are optically inactive. And they are not even mirror images of each other. Then what will these be? These compounds are diastereomers. Okay. Now look at the next one. In next one, what we have, first of all, let's figure out whether these are optically active or not. Okay. So this carbon and this carbon is chiral, this carbon and this carbon is chiral. Okay. Now we have to see whether the plane of symmetry is there or not. The plane of symmetry, there is no plane of symmetry because one chlorine is up and one chlorine is down. So when you cut it, no matter whichever the case, no plane of symmetry. And because they are just next to each other, when you pass a line from one chlorine to another, you will not have another chlorine other side. I mean, there could be center of symmetry if there would be a chlorine over here, but that's not the case. Chlorine is just adjacent to the wedge chlorine. So there is no COS also. No COS, no POS, hence it is optically active. This is optically active. This is optically active, and definitely these are mirror images of each other. Right? These are mirror images of each other, optically active, and hence non-superimposable also. Okay, so these are non-superimposable mirror images of each other, and they're optically active. Hence, these are enantiomers. Now, next compound. In next compound, we have to figure out whether these are again what kind of compounds these are, diastereomers or enantiomers. In question number 7, see whether we have plane of symmetry. First of all, let's figure out whether these have chiral centers or not. So we have chiral centers over here. Then we have to figure out whether the plane of symmetry is there or not. So plane of symmetry is not there because one chlorine is up, one chlorine is down. Here also it's not there. One chlorine is up, one chlorine is down, so no plane of symmetry. Center of symmetry is not there because for this chlorine there is no opposite chlorine over here. Then for this chlorine there is no opposite chlorine over here, so no CO. So these both are optically active, and definitely the mirror images of each other. These are mirror images of each other, so these will be enantiomers. For wedged bond, the mirror image is dash bond. Okay, this is something which you should be knowing, very well. So dash is the mirror image of wedge, and wedge is the mirror image of dash. Now look at the eighth one. Eighth one, COH, H, OH and CH3, COH, OH, H and CH3. These look like mirror images of each other, but we have to check whether they are optically active or not. So it seems like it's optically active because there is one chiral center, and wherever there is this one chiral center, they are optically active. Optically active mirror images of each other and are definitely non-superimposable, and hence these are optical molecules. So I hope you know why these are not superimposable with respect to each other. See, when you're talking about the Fischer projection, we know that COOH and CH3 are away from the viewer, so they are like this. They are like this. They are away from the viewer. And when you talk about the H and OH, they are like this, right? So when you try to impose OH on H, then definitely they are not. I mean, if you place it directly, this mirror image on this molecule, first on the second molecule, if you place on the first molecule, then H and OH will be directly on each other, and hence they will not be mirror images. But if you rotate it and somehow OH comes on OH, in that case also what will happen is for one OH the direction will be inwards, and for one OH the direction will be outwards. So bond direction will be completely different, even though OH will be on OH, so they will not be able to merge and become one. It will be like this. Over one OH here and one OH here if you're trying to superimpose. So that's the reason why they are non-superimposable. So now look at this ninth one. So what is the case over here? In this, what we will do? See. So this molecule, first of all, we will check whether we have chirality in the molecule or not. So this is the carbon which will have chirality. Okay, yeah. So POS is there? No. POS is not there. COS is there? So chirality is there. Now look at this molecule, first molecule and the second molecule. So in the first molecule, chlorine is above the plane, whereas in the or towards the viewer. And then you talk about the chlorine in the second case, it is away from the viewer. Okay. So now if you flip the molecule, what will happen? The molecule, this molecule, if you flip it to 180 degree, what will happen? This will become this. Just try to imagine what I'm trying to tell you. So basically, it's like, let me show. I'll just take a random thing and we'll try to explain. So let's say this is this ring and it has this chlorine away from the viewer. Okay. Now if I flip it to 180 degree, what will happen? This will come up. Okay. So the bond which was here, this side, will come to this side now. So basically I have flipped it to 180 degree. Did the molecule change? No, molecule didn't change, right? So it's just a flipping I have done, and on flipping what we will get the mirror image. This compound and these compounds are mirror images of each other, right? So both of these compounds are mirror images of each other. Both the compounds are individually optically active because no POS, no COS. So these are enantiomers. Okay. Now let's see the next set of questions. Now try out these questions on your own. Again, try to visualize it. More you'll be able to visualize, correct will be your answers. Okay. Try to visualize and then I'll discuss with you. Okay, so let's talk about the case number 10th. So in the 10th question, what is happening is we have a cumulene with on the terminal carbon, hydrogen and CH3 coming outwards, as in like one towards the viewer and one is away from the viewer, like that. And the another C, this C has the hydrogen and CH3 like this. Okay, so one has up and down and one has like this. That's how the structure is. I have already shown you the structure when we were talking about the optical activity. So is this molecule optically active? Yes, because this molecule doesn't have COS at all. Now let's talk about the POS. If I'll cut it like this, then also the plane of symmetry is not there. If I'll cut it like this, then also the plane of symmetry is not there. Though it looks like there are two same groups over here, but these are different. These are in different plane, right? And if you cut the slice cut also, then also there is no plane of symmetry. So no plane of symmetry, so chirality is there. And the same case, chirality will be here also. Now let's see whether the compound which we have got in the other side is a mirror image of it or not. So hydrogen is here, CH3 is here, CH3 is here, hydrogen there is here, and CH3 here and CH3 here is here. So yes, these are mirror images of each other. So these compounds are optically active and are mirror images and are non-superimposable, right? Chiral compounds are anyways non-superimposable. So these are enantiomers. Correct? Now look at the next compound. In next compound, what we have, first of all, we have to see whether we have a chirality in the molecule or not. So when you're talking about the chirality, if you see, if I cut it from here, again, what's the issue? This hydrogen and this CH3 and this hydrogen and this chlorine basically are in two different planes. Okay, so basically one is towards the viewer and away from the viewer like this, like up and down, okay, up and down, and the other one is like this. Moreover, there are four different groups are present. So this molecule will possess chirality. Why? Because there is no plane of symmetry and no center of symmetry. This molecule is also the same. So hence, chirality is there in the first molecule and the second molecule both. And chirality means optical activity is there. Now we have to see whether this is mirror image or not. So hydrogen here, chlorine here, chlorine here, hydrogen here, hydrogen here, chlorine here, chlorine here. This is in one plane. Whichever plane it will be the same plane. This ring will be in, and whichever plane this ring will be in, the same way this plane will be in the same ring. This ring will be in the same plane. So they are exact mirror images of each other and definitely non-superimposable, and hence these are enantiomers. Now look at the next compound. So in the next compound, first of all, we have to see whether the chirality is there or not. So if I cut it from here, what I'm getting is I'm getting the plane of symmetry. So plane of symmetry means no chirality. So first of all, this molecule is not chiral. Look at the other one. Is this chiral? This is also not chiral. So both are not chiral. And it is a mandatory condition for a compound to be enantiomer is the chirality should be there. Okay, so no chirality, that means the relationship, the enantiomeric relationship is not there. Now we have to see whether these are diastereomers or what these molecules are exactly. So diastereomers are must not be the mirror images. So and they should be optically inactive. I mean, they can be optically inactive, they can be anything, okay? They can be optically active, one optically active, one optically inactive. Look at the second one. Second one is like this. If I have taken a molecule, okay, and look at the chlorines over here, both the chlorines are downwards, okay. Now, if I flip this molecule, won't these two chlorines will come up, and 180-degree rotation doesn't change the molecule. This is something which I have already told you before. So, I have rotated the molecule to 180 degree, and what I got is both the chlorines up. Okay, so exactly same thing will happen here also. If I rotate this molecule to 180 degree, will this won't this molecule will have these chlorines upwards, right? So if I'll have the chlorines upwards, then in that case, what it will be? Will it be a diastereomer or it will be identical? It will be exactly identical. Why? Because you just rotate it. This is just kept in some random position. You have just rotated it to see whether these are forming non-mirror images or mirror images or what exactly it is. So rotation, the slight rotation here, the 180-degree rotation will not change the molecule, and hence these two are identical. So what are diastereomers? That even after rotation, no matter wherever you rotate it, how many degrees you, I mean 180 degree you rotate it, molecule will still be a non-mirror image. That's what exactly the diastereomer. So even if you do 180 degree rotation, you won't find the molecule becoming the same thing or mirror image or anything like that. So you make any change in that molecule and it will not make it the mirror image. That is exactly the diastereomer. So diastereomer will be two different configurations altogether. So here the configuration is same. Only difference is here the viewer is in the front and here the viewer is at the back. That's all. You just move the viewer in the front and what will happen? It will be the same compound. It's not going to change. These are two identical. Now look at the 13th one. In 13th one, what is happening? This is in one plane. Let's say this benzene is in a parallel plane to the board, and this will be in the perpendicular plane. So when you draw the mirror image, what will happen? So one set of molecules will be like vertical, and one set. This is how it will be. So one benzene will be like this, flat, in the plane perpendicular to the viewer. Okay, and hence the molecules which are attached over here or attachments will also be coming outwards like this, like this, like this. This is COH, and this is your NO2. That's how it will be, right? And if I talk about benzene, the other benzene, which is on the parallel plane, then in that case, what will happen? Here will be your NO2 and here will be your COH. So in the same plane, like this, right? Got the point. So basically, both this compound is optically active, yes, because there is no POS, no COS. How it doesn't have POS, COS? This is something which we have already discussed earlier. Okay, because if you cut it through this, these groups are in different plane altogether. Okay, so if you cut it, no same thing will come. If you cut it like this, then also no same thing will come. You'll do the slice cut from either way, you'll not get the same thing, right? So this is optically active, and this molecule is optically active. So both molecules are optically active. So enantiomer relationship can build up here if they are mirror images of each other. So we just have to see whether these are mirror images or not. So if you draw the mirror image of this molecule, this will be exactly this. This will be exactly this. So look at it very carefully. This is one which is perpendicular to the plane, and this is one which is parallel to the plane. Alignment of the molecules also you see. This is exact mirror image, and hence this will be enantiomers. So here a little bit of visualization is required, and obviously I'm not going to show you the 3D structures again for these molecules, which we have already discussed when we were talking about the POS and COS. That's the reason why you have to remember their visualization. You should be able to visualize. I am not taking much time here because I already know what relationship they have, but when you are doing it, you have to actually give it some time, think, and then do all switch over, whatever is required, rotation, all check, verify it very well, and then only give it a certain relationship. Okay, because you may get confused sometimes when there is a difference in identical and diastereomers. So identical means after rotation you must get the same molecule, but when you are talking about diastereomers, you won't, after rotation of 180 degree, you won't get the same molecule. So that's exactly what you have to look for. Okay. Now next we are going to talk about the meso compounds, which are third type of compounds. Let's understand what exactly are the meso compounds. So meso compounds, when we are talking about the meso compounds, these are also one type of compounds. It is not a relationship. So it's not like two compounds are meso or something like that. No, it's not a relationship. It's a type of a compound. Okay, it's a property of a compound to be a meso compound. Now, what exactly is meso compound? Meso compounds are optically inactive compounds. They are optically inactive. Basically, they do not show any optical activity. Basically, they do not shift the plane polarized towards right or left. And when you do a certain arrangements in the same molecule, you try to do some switchovers, you will get a diastereomer of the same molecule which will be optically active. So basically, it's one type of isomer of a compound. It's a certain isomer of a compound which is optically inactive, but other isomers would be optically active. Okay, so basically, if I have a compound which can have three different kind of compounds or three different kind of isomers, let me just give you an example. If I have a compound like this, COOH, COOH, HHOH. Okay, now I have two chiral centers, one is here, one is here. I can write this compound as this also. I can do some rearrangements and I can write this compound like this. Please look at it very carefully what I'm doing. So I have just done some rearrangement and I got certain compound over here. Now what can I do? What will I do now? Just try to understand, to check the optical activity. What is the first thing we check? We check whether the compound has plane of symmetry and center of symmetry or not. So though they have the chiral centers over here, we have to check whether they have plane of symmetry and center of symmetry or not. Okay guys, so look at the first molecule. What do we have in the first molecule? We have COH, H and OH, H and OH and COH. Both the hydrogens on one side and both the OH on the another side. When you talk about the horizontal plane, the molecules are like this. When you talk about the vertical plane means they are away from the view. That's how it is. So if I have to show you this Fischer projection, how can I show it? I can show it to you like this. Just look. This exactly is the Fischer projection. So assume this yellow ball is COH. Okay. So this is away from you. You are the viewer. This is away from you. And these are the groups which are present on the horizontal lines, which is towards you. Okay. Now if I have to find out whether this molecule is chiral or not, what is the first condition? Any molecule, to find out whether it's chiral or not, what do? We check the center of symmetry and plane of symmetry. So let's figure out whether the plane of symmetry is there or not. So here, from the center, if I cut it, won't I get two mirror images? This is the mirror image of this, okay? This is the mirror image of this, and this is the mirror image of this. When you cut it from the center, you're going to get the mirror image, and that means this molecule possesses the plane of symmetry. So this particular molecule is what? Optically inactive molecule. Guys, please look at it very carefully. Okay, this is the Fischer projection. I have not done anything. I have just shown you the 3D model over here. These two groups are on the horizontal line, and these groups are on the vertical line. This yellow group you can see is on the vertical line. This is away from you, and this is towards you. So when you cut it from the center, because the two same groups are present over here, when you cut it from the center, from here, from this plane, what will happen? You will get the two mirror images. This part is the mirror image of this part. So this part is mirror image of this part, right? So basically plane of symmetry is there, so optical activity is not there in this molecule. Okay, now look at the other compound. So now in other compounds, do we have plane of symmetry? No, we don't have. Okay, that we have seen. From this molecule itself, you can determine whether the plane of symmetry for the other molecules will be there or not. I'm going to switch over the position. So now if this blue ball is here, if you cut it through any plane, will you get the plane of symmetry? You cut through any plane, are you going to get the plane of symmetry? No, you cannot. Now the question is whether it has center of symmetry or not. In the 2D molecule, it looks like it has a center of symmetry because this hydrogen is opposite to this and this OH is opposite to this. But you look over here. If I pass a line through the center, okay, it's like this. If a line passes through the center here, does this join this and this hydrogen? Or any line which is joining this hydrogen and hydrogen, is it passing through the center? No. The line joining this molecule and this molecule, is it passing through the center? No. So the line which will pass through the center is nowhere even coming closer to the same group on the opposite side. So though it looks like from the 2D structure that it should have a center of symmetry, but it doesn't have. Just look at it very, very carefully. This, if I draw a line, this is the line, my hand is the line between this molecule and this molecule. Is it passing through the center of the molecule? No, this is from where I am holding, this is the center of the molecule, okay? But my hand is not passing through it, no, it is just simple straight. And if my hand will pass through the center, let's say I am passing my hand through the center, this side should be the area where I should be getting this white ball, which I am not getting. This is somewhere here in between yellow and white. So no center of symmetry is there. So no POS, no COS, so optical activity is there. Yes. Now look at this molecule. What is the configuration here? Let's see the configurations also. So this is first group, then this is second group, and this is the third group down here. So this is how we'll go, and this is clockwise rotation, and hydrogen is on the horizontal line. So the configuration comes as S. Similarly, come from here. This is 1. This is 2, and the upper group is 3. I go from here 1 to 2 to 3. This is again clockwise, and configuration is what? Clockwise configuration is S. Okay, exactly same way. If I try to do it in this is 1, this is 2, this is 3, the down one is 3. So 1 to 2 to 3, anti-clockwise R. Again here 1, 2, and 3 on the top as in the other group. Okay. So if I go from 1 to 2 to 3, again anti-clockwise R. So these two have, the first one and the second one, have exactly opposite configuration. Both are optically active and both are mirror images also. If you see, I have made it quite messy, but if you would have noted the earlier group or earlier example, the time when I had written it neatly, at that time if you would see, these are mirror images of each other. So the relationship between this group and this group is enantiomeric relation, which I have explained you in the last video, last part just now. But what about this? This is also a type of the same molecule, the isomer of the same molecule. But what is the problem here? That it has POS, right? And that is the reason why it does not possess the optical activity. Because it has a plane of symmetry and we can cut it into 2 equal halves, this is optically inactive compound. So this compound is a Meso compound. Does it has a diastereomer, non-mirror image, non-superimposable compound which is optically active? Yes. This second compound and the third compound are non-mirror images, non-superimposable, and the relationship between first and second is diastereomer, and first and third is also diastereomer. One compound, one diastereomer of it is optically active, whereas the first one itself is optically inactive. So this exactly is the condition for a compound to be meso compound. So what does the meso compound say? It is an optically inactive compound which must have at least one diastereomer which is optically active. Okay, and as I said, meso compound is nothing else but an isomer of same type of compounds. The arrangement has been done in such a way that it gets a plane of symmetry, and due to that plane of symmetry, it becomes optically inactive. There is, we can say it in one more way, that if you look at the configuration of the molecule. If I want to write the configuration of this molecule, this is 1, 2, and 3. 3 the lower group. So I'll go from here to here. What is it? It is anti-clockwise. It is anti-clockwise. The configuration will be R. Okay, if I try to find out the configuration for the second one, the second carbon down here, it will be 1, 2, and 3 the above one. So if I go from 1 to 2 to 3, what kind of rotation it is? It is clockwise. So configuration is S. Now if you look here, the above carbon and the lower carbon has opposite configurations. So basically what happens is, when the light passes through this molecule, you can say through the plane of symmetry, it is optically inactive, or actual reason is because they contain the opposite configuration completely. Because they have the opposite configuration, this molecule passes the light towards, when the light passes through it, plane polarized light passes through it, half of the part of the molecule tends to shift the light towards right, and other half of the molecule tries to shift it towards the left. And because the angles are exactly same, because the angles through which they rotate is exactly same, when the light comes out of the compound, you will find there is no change in the orientation of plane polarized light. Why? Because their effects have got nullified with respect to each other. The above molecule, the first half compensated the second half, and second half compensated the first half, and that is the actual reason for optical inactivity. So this is what exactly your meso compounds mean. So let's quickly see in the definition what all is written. In meso compound, there must be 2 or more identical substituted stereocenters. So this is also a mandatory condition, that for a compound to be meso, it must have 2 chiral centers. 2 chiral centers. So if it doesn't have 2 chiral centers, then the compound cannot be meso. Okay, and it will show the internal symmetry plane. That means again POS, which will divide the compound into 2 halves. These 2 halves will be the internal mirror image of each other, and because they will be mirror image, their stereochemistry or the rotations done by first half and the second half will get cancelled out, and that will be the reason of optical inactivity of that molecule. Okay, so that exactly is what we have written. We have all type of compounds which can be meso. We can have cyclic compounds which can be meso. We have open chain compounds which can be meso. So any type of compound can be meso. The condition is it should have 2 chiral centers minimum, and its one diastereomer should be optically active. Okay, at least one diastereomer must be optically active. So what is the identification? As I mentioned, if a compound A is a meso compound, then it should have 2 or more stereocenters. This is the first condition. Second condition is when you mark their RNS configuration for wherever you can mark it, the one half will have R and another half will have S. So they will have opposite configurations in their molecule. Apart from that, I told you when you look at the plane of symmetry, they should form the mirror images of each other. So this is, and the third condition is it's diastereomer. It's another form. Another isomer of the same molecule must be optically active, then only a compound will be called a meso compound. So look at this. Look at this compound. This compound is OH, HCl, HCl, OH. So both of these compounds have that plane of symmetry. I can form one more compound of the same type, of same molecule. What I can do is I can put chlorine here, hydrogen here, and chlorine here, OH up and OH down. If you talk about this particular compound, which is the isomer of these 2 compounds which I have mentioned above, then this is optically active. And that is the reason why these compounds will be called as meso compounds. Now let's see some examples of meso compounds. So here I have shown you this compound. This is meso 2,3 dibromobutane. Why it is meso? Look at the molecule very carefully. In the molecule, what all we have done? In the molecule, we have hydrogen, bromine, CH3, bromine, CH3, and hydrogen. So this is exactly this molecule, and we've already discussed why this molecule is meso, and exactly is the reason for these compounds. So they have internal plane, or you can say they have POS, identical stereo centers are there. They are forming, when you cut it through a plane, they are forming the mirror images, and that is why this compound is a meso compound. Now look at the next compound. Look, next compound is also exactly same. So see, I have just shown you this, and many of the compounds you'll be able to identify using this structure itself. Okay, this is your methyl, this is your methyl, this is your hydrogen, hydrogen, bromine, bromine, and then cut it from here, and they'll form the two equal halves, which are mirror images of each other. And when you look at their configuration, one will be R, another will be S, and due to the internal compensation, they will be optically inactive. Okay, now look at the third one. In case of third one, first of all we will check, as I mentioned, we have to check first whether the chiral centers are there or not. Two chiral centers are required for a compound to be meso compound. So this molecule has a chiral center. First of all, this molecule itself doesn't have any chiral center. You go to this carbon, go to this carbon, go to this carbon, go to this carbon, none of the carbons are chiral centers. So basically, there is no possibility of this compound being a meso compound. Okay, and apart from that, let's see one more thing. If I change the configuration a bit, so what will happen? It will form a diastereomer. So if one chlorine is coming towards the viewer, one is away from the viewer, that is a diastereomer of it. So second condition was that the diastereomer must be optically active. So we will see this itself is not optically active. Why? Because POS is present over here. Now look at the another compound which I have formed by changing the configuration. Is it optically active? No, because it has plane of symmetry also. You cut it through this plane. Half of chlorine will go this side, half of chlorine basically. If I cut the slice cut from the top, what will happen? The chlorine which is towards the viewer, half will be this side, half will be that side. The chlorine which is away from the viewer, half will be this side, half will be that side. So plane of symmetry is there, so optical activity is not there. In fact, here there is a center of symmetry also. Okay, so both are optically inactive. That is why, even though it looks like it should be meso, but it is not meso due to two reasons. First of all, it doesn't have the chiral centers. Second thing is its diastereomer is not optically active. Okay, even if it would be one reason, only single one reason that it doesn't have chiral centers, then also we would have said the same thing, that it is not a meso compound. So you should be able to identify whether the compound is meso or not. This is very important. Just don't go by that, okay, the configuration is same up and down, or it looks exactly same, or when you cut it, it is giving you the plane of symmetry, and it is becoming non-chiral, and hence it is meso compound. No, we also have to check whether its diastereomer is optically active or not. So this is a very important condition. Now let's talk about next set of questions. So I have a compound over here. So does this compound has a chiral center? Yes, this is the chiral center and this is the chiral center. Does this molecule possess chirality? Let's figure out. If I cut it through this plane, the plane which I have mentioned, then it is POS, so no chirality. Now, whether this compound is meso or not, we have to figure out. Why? How can we figure out? Two conditions are matching. POS is there, two chiral centers are there. Now we have to see whether its diastereomer will be optically active or not. So I have formed a diastereomer of it. What is the diastereomer here? This is the diastereomer. I can just change the configuration of one of the chlorine. One will go up, one will go down. And it has two chiral centers. No POS is there, no COS is there. Hence optically active molecule it is. So these two, when I'm dividing it from here, it is giving me two equal halves which are mirror images of each other. So yes, this is a meso compound because there are three conditions. All the three conditions are getting fulfilled. Two chiral centers, plane of symmetry is there, which is breaking it into two equal halves, and third is its diastereomer is optically active. Now look at the fifth compound. In fifth compound, what is happening? First of all, we have to find out whether we have chiral centers or not. So if you look at this carbon and look at this carbon, no chiral centers at all. So first of all, chiral centers itself is not there. Secondly, when you talk about the even membered chain, though I will cut it from here and I'll get two equal halves, but because there are no chiral centers, what will happen? The possibility of this being meso is not there. I'll draw its diastereomer. What kind of diastereomer I can get from this? I can get this kind of diastereomer. When I can change the configuration of one chlorine. This is diastereomer. But will this diastereomer be optically active? I don't know whether you remember this or not, but when we were talking about the optical activity, at that time I told you any even membered ring no matter it is having a cis conformation or trans conformation, when the same groups are in the completely opposite direction, it will possess at least POS. So you can cut it through a plane so that this you can cut it from here, and the half of chlorine will come here, half of it will go here, half of it will go here, half of it will go here. So basically towards the viewer wala thing also will be half here, half there, and towards away from the viewer chlorine will also be one half this side, one half another side. So POS it will have, and hence it will be optically inactive. So its diastereomer is also inactive. Molecule doesn't have chiral centers, so this compound cannot be meso. Okay, now let's look at the sixth one. Tell me whether it's meso or not. What can happen over here? I can cut it from the center. All these are chiral centers. This has three chiral centers. If I'll cut it from the center, what will happen? It will form meso. If I change the configuration of one of it, let's say bromine is here, bromine I shift here, and hydrogen I shift here, it will become a diastereomer, and diastereomer is also optically active because it doesn't have POS or COS. So from this plane, when we make diastereomer, there will be no POS, no COS, and hence that will be optically active, and that is the reason why this compound is a meso compound. Exactly same way here, you cut it through this plane. Do we have chiral centers? We have 4 chiral centers in this molecule. The POS is there in this molecule? Yes, there is. Now we have to check whether its diastereomer will be optically active or not. You change any one configuration, you shift OH here and hydrogen here, and what will happen? It will not have plane of symmetry, it will not have center of symmetry, and it will become optically active. That means this diastereomer is going to be optically active, and hence this compound is a meso compound. Now look at the seventh one. In seventh one, we have to figure out this is meso or not. So first of all, we have to see whether the plane of symmetry is there or not. So plane of symmetry is there through this plane, and we can cut and get the two equal halves. We have chiral centers. Yes, this carbon and this carbon are chiral carbons, right? Now we have to see whether its diastereomer is optically active or not. So let's draw it. So its diastereomer is gonna be one chlorine like this and another chlorine like this. Now there is no way you can cut this molecule in a slice cut and you can get towards the viewer chlorine half here, then towards and away from the viewer chlorine half here, half there. That is not possible. We can cut it through like this, but is it giving me the two equal halves in the mirror images of each other? No. So this molecule doesn't have POS and COS. Though we have already spoken about this molecule in detail when we were talking about the checking of chirality and optical activity. If you don't remember how exactly this is chiral, you can go back and check. Okay. So does it have center of symmetry? No, it doesn't have center of symmetry also, because for center of symmetry I would need this chlorine to be somewhere here, that too with the opposite configuration. So that's not there. And all these things you can just quickly think and then figure out whether this is optically active or not. So this is optically active molecule. This is optically inactive due to the plane of symmetry. It has two chiral centers, so this molecule is gonna be meso. Now look at this. Is this meso or not? If I cut it from this plane, I'll get two equal halves. It has chiral centers. Yes, it has chiral centers. So two chiral centers are there. Now we have to check whether its diastereomer will be optically active or not. So let's draw it. Chlorine here and chlorine here. No plane of symmetry, no center of symmetry. So this is optically active. The diastereomer is also optically active. So this is meso. Look at this compound. This also will behave in the same way. You cut it from here, it will get the plane of symmetry. Optically active it is. It has two chiral centers. So two conditions are fulfilled. Draw its diastereomer. Its diastereomer will be something like this. My bad, my drawing is really poor. So I can draw it like this and like this. And this molecule neither possess POS, not possess COS, and hence it is optically active. Okay. Cut it from here, you won't get two equal halves. You pass through the center, then in that case, methyl should have been here, but that's not the case. So basically, this doesn't contain COS or POS. It's optically active. So its diastereomer is optically active. Hence, this compound is meso. What about this? This has two different groups at these places. So when you cut it through the center from a plane, will it give you two equal halves? No. So this cannot be meso at all. We don't have to even check for the diastereomer. So this is how exactly we check whether the compound is meso or not. This is what exactly you have to think. You have to keep your mental eye open. You have to visualize properly I have given you so many examples in case of POS, COS and optical activity so that you learn how to visualize. And wherever it is required, you can use all those structures and their appearances. I have shown you it in the 3D diagram also so that it becomes easier for you to visualize. So now going forward, I won't be taking so much of time in explaining how the molecule will look like in a 3D representation. That is something that you have to think on your own and solve the question. In next video, we will be talking about excess of symmetry, and we will be talking about what exactly is D and L configuration is. We are almost on the verge of finishing off this optical activity, hardly 1 or 2 classes it will take to finish it off. So majority part is done, and I hope you would have understood the basics. If you still have any doubt, ask me in the doubt section.